Hi guys, this is a calculus video to be watched Thursday, March 2nd. There's going to be no homework for it, but write this down first. And we're actually, guys, going to do notes for 7-7 and 7-8 in this same video. So, direct proportionality versus inverse proportionality. So if you hear that y is proportional to x, okay, so write that down if you want to. Y is proportional to x. Then if they just say proportional, that means directly proportional. Sometimes they might say directly proportional, but if they say proportional, it implies directly proportional. And for y to be proportional to x means this: y equals k times x, where k is some constant. Okay? And then inverse proportionality, which comes up a lot less, if you hear that y is inversely proportional to x, if they mean inversely proportional, they'll have to say it. Otherwise, it would imply directly. So if y is inversely proportional to x, then y would equal k over x. Again, where k is a constant. Okay, so let's translate some. We're going to translate two sentences into math, and then we're going to move to the page with video 7-8 on it. So this is also for Thursday 3-2, and this is video 7-7 continued. Okay, so direct proportionality. The rate of change of p with respect to t is proportional to 10 minus t. So the first thing I'll do is I'll write down the direct proportionality formula. So I've got y is equal to kx, and then I'll leave blanks where y and x were. So what is directly proportional to what? So the rate of change of p with respect to t. So that's what's going to go in for y. So dp dt. So dp dt is directly proportional to what? Is proportional to 10 minus t. Okay? So we've translated that sentence into math language. Inverse proportionality. The rate of change of q with respect to t is inversely proportional to the square of t. All right, so since they said inversely proportional, we're going to use this formula. So y equals k over x. And just like before, I'll leave blanks for y and x. So blank is inversely proportional to blank. So what goes in these blanks? The rate of change of q with respect to t, that's what would go here. So dq dt. So dq dt is inversely proportional to what? Is inversely proportional to the square of t. The square of t would be t squared. Okay, so that's how you would translate that. Okay, now we're going to move to page 15. Okay, so this is page 15. So video 7-7 is going to include this page. So exponential growth and decay model. If y changes at a rate proportional to the amount present, okay, meaning dy dt is directly proportional to y. Okay, so the rate of change of y with respect to t is directly proportional to y. Y equals y sub 0 when t equals 0. I think this is called y not or something. I'll just say y sub 0 because I'm not really sure how to say it. Then this formula is true. Okay? All right, so guys, anytime that we have this fact, every time we can establish this relationship, we are then going to be able to say that relationship. Okay, where k is the proportional constant, sometimes called the constant of proportionality. Exponential growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. So let's do this example. The rate of change of y is proportional to y. Okay, so I know it is proportional to, so I'll write down y equals kx. All right. So what is proportional to what? The rate of change of y. All right, so the rate of change of y. And then, guys, when I read a little bit further, I see that t would be the independent variable. So lots of times x is the independent variable. Here they're using t for the independent variable. So the rate of change of y with respect to t is implied. So dy dt is directly proportional to what? Is directly proportional to y. So guys, anytime you have the rate of change of something directly proportional to that same something, so you've written this equation, then you're allowed to say this. Okay, so I'm going to say, therefore, so then we have y equals y sub 0 e to the kt. Okay. Now y sub 0 is going to be the y value at the t value 0. So they're telling us this, that when t equals 0, y equals 2. So I can right now make this a more specific equation. Oh, I haven't even read the rest of it, sorry. So this is the problem we're solving. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? So we have to come up with an equation, a function, that will give us the y value at any value t. And we will have this equation when we have filled in two constants. So this constant here, which we know is 2. But then this constant k we also have to know. Well, we need to find two constants, so we were given two conditions to do that. We had this first condition, which allowed us to get that, and now we have this second condition, which is going to allow us to get k. Okay, so I'll go over here and I'll say, since t equals 2, I'll say since when t equals 2, y equals 4, comma, 4 equals 2e to the 2k. All right, I plugged in 2 for t. Okay, so now we've got to solve for k, and then we'll be able to put it in there, and then we'll have a function that will give us, for any t that we plug in, it will give us a y value. Alrighty, so e to the 2k, I'm dividing both sides by 2, so I get equals 2. And then, so if you could think of this however you want, guys. You could either take the natural log of both sides to knock down this exponent, or you could just convert to log form or unroll the log. I think that's how some of you think of it. So in either case, we'd end up with the natural log of 2 equals 2k. So we've got that k equals the natural log of 2 over 2. Alrighty? And then we can say, therefore, y is equal to 2e to the, put this in for k, to the natural log of 2 over 2t. Alright, so this function here will give us, we could plug in any value of t and it's going to give us the y value. Okay, so and then I'll say, therefore, we want the y value for the t value 3. So I'm going to plug in 3 for that. And I already did this. And then, I mean, you could just leave it like that, but let's get a decimal. So y equals, I got 5.6569. Okay. So that's how you solve that. Now, guys, you could have figured this problem out without knowing this formula. That's how I've had some students do it in the past, but it's a huge pain. You'd have to first write down this differential equation, then separate the variables, so multiply both sides by t, get the y over there, take the antiderivative. It's a lot easier if you could just recognize that whenever you write a formula down like this, that this formula, a formula like this that says the rate of change of something is a constant times that something. When you write that formula down, you can immediately write that formula down. And then you won't even have to take any antiderivatives at all. So there's that. Now, moving back to this page, we're going to solve a problem. Now, guys, down here, so let's see this. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 lines here. Let's go down a third one up from the bottom where it says of rabbits. Okay, so right there, of rabbits. Please put in infected rabbits. Okay? And you'll see what I'm talking about in a moment. Alrighty. So, in Australia, a genetically engineered bacterium that infects rabbits was being developed at an island laboratory. The scientists were not planning on releasing the bacterium, but in 1995, mosquitoes carried it to the mainland and infected rabbits there. Once the bacterium was on the mainland, the rate of increase, okay, so now as soon as I hear the word rate, they're starting to talk about calculus. The rate of increase in the number of infected rabbits was proportional, okay, that means directly proportional, was proportional to the number of infected rabbits. Okay. Express the preceding sentence in symbols, all right? So this is direct proportionality. So I'm going to write down my formula. So I've got y equals kx, blank equals k blank. Okay, so what is directly proportional to what? So the rate of increase in the number of infected rabbits. Okay, so maybe I'll do this. I'll say let I equal number of infected rabbits, all right? So if I is the number of infected rabbits and the number of infected rabbits is changing with time, then the rate of increase in the number of infected rabbits, that would be di dt, okay? So di dt is proportional to what? Was proportional to the number of infected rabbits. Guys, that's what I let be the number of infected rabbits. So di dt equals k times I. And here we have that situation that we just talked about on the previous page where if y changes at a rate proportional to the amount present. So we've got I changing at a rate proportional to the amount present, okay? So we have that the rate of change of I is directly proportional to I. And in this situation, we can conclude that I is equal to I sub 0 e to the kt, all right? So just like that before, we can conclude that. So just like that. Alrighty. Now let's keep reading. Suppose that initially 20 rabbits were infected. So I'll do a table. Tables are nice. So T and I. So initially 20 rabbits were infected. So initially would be at time 0, we had 20 infected rabbits. Guys, okay, never mind. And that 3 weeks later, there were 53 infected rabbits. So 3 weeks later, there were 53 infected rabbits. How many infected rabbits will there be after 40 weeks? So at time 40, that's what we want to know. So guys, we have to figure out a function here that will give us the number of infected rabbits if we plug in t. So we've got to figure out what I sub 0 is and what k is, the constant of proportionality. So if we're going to figure out these two things, they need to have given us two conditions, which they did. So I sub 0, that's just the number of infected rabbits at time 0. So that's 20 e to the KT. Now we've just got to find K, so we'll use this condition here. All right, so this condition. So off to the side, I'll say when t equals 3, I equals 53. And then, so the result of this is that 53 equals 20e. I'm plugging in 3 for t, so we get 3k. And then, so this is e to the 3k. And if you don't understand anything I do, please stop and think about it. So I divided both sides by 20. And then we have that 3k is equal to the natural log of 53 over 20. So we've got that k is equal to the natural log of 53 over 20 over 3. Alrighty, so back over here, this formula, guys, is really great. This going from here to here, it avoids so much work. All right, so therefore I can say that I is equal to 20 e to the natural log of 53 over 20 over 3t. Okay, so this function is going to give us the number of infected rabbits at any time that we want. All right, and they want me to plug in t, so therefore I is equal to 20e to the natural log of 53 over 20 over 3 times 3. Ugh, wait a minute. Did something go wrong? No, we're good. No, I plugged in the wrong thing. Yes, duh, I want to plug in 40. Sorry, guys. I want to plug in 40. I want at 40 weeks. Okay, so right there. So I did do something wrong. And I plugged that into my calculator earlier, and I got this. This infection is spreading like wildfire. Okay, and now let's use units, guys, all right? So this many infected rabbits at 40 weeks. Okay, so that's that, and I will see you soon. Okay, no homework, and see you soon. Bye-bye.